The title of this section, guys, it's called Goodness of Fit Test, GOF. And let me tell you what this test is about and what do we test. If I have two proportions, guys, P1 and P2, I can test the difference between two proportions. You already learned that in chapter 8. And we tested using what we call two proportion Z test. You still remember that, right, guys? In chapter 8, we tested the proportion, the difference between two proportion, P1, P2, using the two proportion Z test. And you would state that P1 equals P2 or P1 not equal P2, P1 greater than P2, P1 less than P2. Well, so if you have two population, if you have two samples, we can use a two proportion Z test. But what about if I have more than two proportions? For example, guys, let me give you this example. A teacher makes this claim. The teacher says that in a typical class, the distribution of the grades in a typical class is the following. 22% receive an A. 30% receive a B. 20% of the students receive a C. And then 5% or 10%, I'm gonna make it receive a D. How many do we have already, guys? 52, 72, 82, and what's left for the 100%? 18% receive an E or a failure in the class. My question to you guys, how many proportions do you see here? Can someone tell me? Okay, you counted 5. 1, 2, 3, 4, 5. I agree. How, if I want to test this teacher's claim, I want to test his claim, whether it is valid or not. I cannot use any of the tools that we already learned to test this one, because the best tool that I have is from chapter 8, which would allow me to compare 2%, two proportions, but here I have 5 proportions. When I say proportion, means the percents, guys. 5 proportions. There is no way that I can use what I learned in chapter 8, to do this, because that involves 5 different population. A population of students who get A, population of students who get B, population of students who get C, population of students who get D, and population of students who get E. So there must be a way to do that. Well, the good news is there is a way to test this, which we're gonna, no mean here. It's all proportions. Forget about the mean. It's all proportions. It's all about proportions. Even if you want to find the mean of what? And I don't have any data other than percent. So it's all proportions. So when you have more than 2 proportions, guys, and you need to test a claim that someone made, this teacher is making this claim. He said, well, in any class, here's a distribution of my grades. And you want to check if his claim is valid or if this is how his grades are distributed. We have to use some tools. And this tool, it's called the Goodness of Fit Test. And it is abbreviated, guys, in your section 10.1 as a GOF test. Actually, it is built into the calculator. So what I'm gonna do, I'm gonna come up with an example and show you how to work it out. You might find it easier even than the procedures that you learned in the previous chapters. It is a little bit time consuming, but it's very, very straightforward procedures. So can we agree that this goodness of fit test can be used when we have more than 2 proportions? 2, you go to proportion 2 proportion Z test. More than 2, you have to go to goodness of fit. More than 2 proportions. Or if you want to say 3 or more. So this is when you use the goodness of fit test. Okay, in the previous chapters, guys, we use the Z distribution, which looks like this. This is the 0. The tails are almost touching. This is the Z. We use the T distribution. Do you guys see the difference between the 2 graphs that I graphed here? What do you notice the difference is? Can someone remind me what's the difference between the Z and the T? Yeah, line is not touching. There's a thicker tail, exactly. So we use the Z, we use the T. That's what we've been talking about throughout chapter 7 and 8 and 9. Z or ZT, ZT. Now, guys, it's going to be a different distribution that I'm going to introduce to you. And let me show you what this distribution is going to be. We're going to introduce a new distribution. It's called Chi-square distribution. And we abbreviate this like that, guys. Chi-square. And let me sketch this distribution and tell you about its property. Okay. What is one thing you notice about this distribution that is different from the previous two? Let's see, guys. Oh, starts at 0, so no negatives. You see, this distribution, guys, starts at 0, so there are no negative values. Whereas in the previous distribution, as you can see, I could get a negative test statistic. I could get Z equals negative 1.72. It's okay, you get negative values. Here, for T, you get negative values. With chi-square, no negative values. So chi-square is always, this is how we write it, guys. Just like the chi, it's a Latin letter and it's always greater than 0. Okay, what else do you notice? Anything else different from the two distributions above? There is. Let's see, let's brainstorm and tell me what. So it is always greater than 0. Well, all of them has X and Y. This is the X here and this is the Y. You can raise 1. Ah, right tail. This is a tail distribution, skewed to the right, always. So this distribution is always a right tail distribution. Very good. And the total area under the curve is always equal to what, guys? We should know the answer by heart. What's the total area under the curve? It's always 100%. 1. Very good. Okay. Now, this is like the T distribution. It has a degrees of freedom. I want to show you 3 sketches of this one when we change the size of n. This is how the degrees of freedom works. The larger the size of the sample, the closer this distribution will become to the normal distribution. For example, if n is 15 here, this is how it looks like. Now, if I make n, guys, 29 or 30 or 31, it will become closer and closer to normal distribution. So it does require a degrees of freedom. for this one. So there is a degrees of freedom that you need in order to find the test statistic. And I'll tell you what the degrees of freedom here is in a second, once we start doing an exercise. So again, it is always a right tail distribution. It's always a positive. The total area under the curve is equal to 1. So when you sketch this distribution, guys, you just do this. Simply do that. And just do a right tail distribution like this. That should be your chi-square. And the good news for section 10.1, you don't get confused whether you do a right tail test or left tail test or two tail test. It's always a right tail test. And I'm gonna walk you through the process of doing this in a second. I'll walk you through the steps. We do one by hand, and then we do one using the, and then we do it again using the calculator. So now you understand what kind of distribution we're gonna be using to solve those problems. Actually, it's called chi-square distribution. And I think we're ready now to introduce how you perform this test. It's gonna be 5 steps, guys. It's just like before, but it's gonna be slightly different, the way you calculate the test statistic. So I'm gonna go now to the handout that I sent you and get the exercise from there. Just 1 second. So section 10.1, chi-square distribution. The shape of the curve, guys, you already understand. You just graph the curve and make sure that you do one that has a tail toward the right. Total area under the curve is equal to 1, as I said. You don't need to take those notes, guys, because you already received this handout. So I'm just gonna fill in the blanks here. The chi-square curve starts at 0 on the horizontal axis and extends indefinitely to the right. As you can see, the tail approaches the x-axis, but it never touches there. The chi-square curve is right skewed, as we discussed. And as I said, the last statement I make, as a number of degrees of freedom becomes larger, chi-square curve look increasingly like normal curve. And to sketch it, you just sketch it like the way we did it. Let me see if the ink works here so I can. It's not allowing me to do ink here. Anyway, okay. So we're gonna do an exercise here for the goodness of fit test. It's right here. This is the example, guys, and you're gonna learn every single bit of the test through this example. A teacher figures that the final grades in the chemistry department are distributed as A, 25% of students, B, 25% of students, C, 40% of the students get C, 5% get D, and 5% get F. At the end of a randomly selected semester, the following number of grades were recorded. Determine if the grade distribution for the department is different than expected. So they're making this claim that the grades are distributed as 25%, 25% for B, 40% for C, 5% for D, 5% of F. And the question is, we want to determine if the grade distribution is still the same or is different. It has changed. It's not the same as I just stated for you guys. So I'm going to walk you through the steps and how to state HO, how to state HA, and so on and so forth. Let me just pause for 1 second. What I'd like you to do, guys, can you write those percentages right here, please? The A, B, C, D, E, F, and just also do this table on a scrap paper. Just write those numbers. grade A, 42 students, grade B, 36 students, etc. Let's do this for a second, please. Let me show you how to work out this problem. Okay. As you know, in any hypothesis test, guys, you have to state the null and the alternative hypothesis. Here's what the null hypothesis is. Always the distribution of grades is as claimed above. That's what HO always. Can someone guess what the alternative hypothesis would be? It's the total opposite. So what would you say in words, guys, here? Let's see if someone can type in an answer. It's different. Very good. Okay. The distribution of grades has changed, you can put, or is different from the claimed one. If you want to use has changed, that would be fine. Okay, guys, now my question to you. Where is the claim? The question is, determine if the grade distribution for the department is different than expected. Yes, it's the alternative hypothesis. Okay. Now, guys, this is the big step. This is where most of the work is done. We're gonna find the test statistic. It's not Z, it's not T, it is chi-square. And I'm gonna walk you through the steps of calculating the test statistic. It is long, guys, but it is easy. And I usually provide you with this blank table, you fill it in, so it will be very easy to just fill in the blanks, you know, and compute the test statistic, which we will talk about after I finish, you know, this table. So you create a table. I have 5 categories here, A, B, C, D, E. I put them here, A, B, C, D, F, right here. As you notice, you see the letter O here. O means the observed values. The observed values is the data that we collect from people. We observe people. So it says here that we surveyed the following number of grades were recorded. So these are the observed values. We noticed for this department that 42 students got an A, 36 got a B, 60 got a C, and so on and so forth. So this is all called the observed values. It's the data that you collect. So you put them here. 42, 36, 60, 8, and 14. Now, guys, so this is observed. Now this is expected. Okay. What's the total here? Can you guys tell me what the total is? You can just add them up. I got 160. So N is total, I have 160. All right. Let me tell you what the expected values are, and then I want one of you to tell me how to find them. The expected value are how many would have gotten an A, B, C, D, and F if the claim was correct above. If 25% would get an A, if 25% would get a B, if 40% would get a C, if 5% would get a D, if 5% would get an F. So how would I compute the expected values, guys? So how many, if this claim was true, how many would I have gotten an A? How would you do it? Any ideas? Oh, it's 20, Ryan, it's 25%, not of 42. It's 25% of the total. What's the total? 160, exactly. So look, guys, this is 25% of 160. And how do I do that? I just do 0.25 times 160, which is 40. I think, guys, you know what to do with the next one. For the B's, is 25% again, times 160, which is 40 again. For D, FC, 40%. You write 0.40 times 160, which is 64. For D, 5%, 0.05, not 0.5 times 160, guys, which is 8. Oh, got the same number. Look, 8 and 8. That means probably the claim is valid. I don't know. If the numbers are very close, probably the claim is correct. It did not change. And here 0.05 times 160, which is 8. Okay, a question for you guys. Without adding those numbers, the expected value, what's the total should be for all expected values? 160, very good, yeah. The observed and the expected are exactly the same. They should be a match, 160, 160. Okay, before I proceed, guys, actually, this is the most important point to learn how to find the expected values. Once you learn how to find the expected values, you're gonna see everything is gonna unfold. So is it clear how I did the expected value? It's a percent of the total. The common mistake that my students make always, they do a 0.25% of 42. No, we do a percent of the total always. So it should be 0.25 of 160. 160. How did I get 160? If you ask me again, I added those numbers. So when I add them, I got a total of 160. All right. Now, let's continue the table. I think you know what to do, guys, for O minus E. O minus E means you need to subtract E from O. Probably you're wondering why I'm doing this table. You will know in a second why we're doing this table. So what's 42 minus 40? Is 2. 36 minus 40 is negative 4. 60 minus 64 is negative 4. 8 minus 8 is 0. 14 minus 8 is 6. And actually, guys, if you add the O minus O's, you're going to get 0 again. Next step, O minus E quantity squared. I'll let you do that. You should know how to do this, guys. So 2 squared is 4. Negative 4 squared is 16. No negative numbers here anymore. Negative 4 squared is 16. 0. And then 6 squared is 36. Now O minus E squared, sorry, let me just fix this one, divided by E. So O minus E squared divided by E. So that would be what? 4 divided by E. What was E here? 40. Here it will be 16 divided by E, which was 40. 16 again, guys, divided by E, which is 64. 0 divided by E over 8. And 36 finally divided by E over 8. Any questions so far, guys? I'm ready to tell you what the test statistic is now. Any questions about the table, just how to work out the details in the table? Actually, when you go and check the book and the homework, you're going to see that he does this table in every single exercise. He shows you how to do the work using this table. Okay, so now what is the test statistic? Here's the formula for the test statistic, guys. It's the sum of O minus E squared divided by E. So can a student tell me how am I going to find the test statistic? Why did I do the table? What do I do to find the test statistic? Any idea? Oh, 0.25 is 25%. No, we're not going to graph anything. What is the test statistic? I said it is the sum of O minus E squared divided by E. You see this column here? It's called O minus E squared divided by E. You just add them up and you get the test statistic. So I'm going to just add up all of those. That will be your test statistic. So it's 4 over 40 plus 16 over 40 plus 16 over 64 plus 0 over 8 plus 36 over 8. What I like you guys to do, just plug them into the calculator, add them up, and give me the answer. So 5.25. So we did step 1. We did step 2, which is a lot of work in step 2 to get the test statistic. Now I'm going to show you how to make a decision. I'm going to use 2 methods, critical value and the p-value, and both of them are easy, guys. You will see. So this is the critical value approach. You draw the curve. You start at 0 always, and you draw like that. Scoot to the right graph. This is the chi-square distribution. And it is a right tail test, shade an area to the right always. That's a nice thing about it. It's always a right tail test. So, and then you put chi-square 0, which is the critical value here. And I'm going to show you how to find this critical value using a table called table 6. Okay, alpha is 0.01. Remember, guys. So alpha, we need alpha, which is 0.01. Okay, so I'm going to move the screen and show you a different screen in a second, which is table 6. So just give me a minute and I'll show you the table and show you how to use it. It's very easy to use table since it is a right tail test. This is table 6, guys. This is the chi-square table. And it's designed to be a table for a right tail test. So you guys, you don't need to change anything when you use this table. You just use it as is. That's the beauty of section 10.1 and actually section 10.2. They are all right tail tests. So you do nothing but just look at the table and figure out the value. Okay. What is alpha, guys? Alpha is 0.01. So I'm right here. This is alpha. Now the degrees of freedom. I have to tell you what the degrees of freedom are. The degrees of freedom for goodness of fit test is the number of categories minus 1. How many categories did we have in the example that we're working on right now? Can a student tell me? Let's see what. 5. So Ryan, 5 minus 1 would be what? 4, exactly. So it's number of categories minus 1. So I'm right here, guys. This is 4, and this is 0.01. So you can see what the test statistic is. It's 13.27. The critical value is, sorry, it's 13.277. That's what it is right here, 13.277. So degrees of freedom, if number of categories minus 1. It's all in the handouts. So that will be 4, 5 minus 1, which is 4. And my critical value, again, guys, look, 0.01 and scroll down to 4. It's 13.277. Okay, I'll go back to stop sharing, take you back to the original handout, and then we'll continue. There you go. You notice, guys, I put the critical value right here, and now we're gonna make a decision. 5.25, where do you think 5.25 is going to be? Before 13.277 to the left or to the right of 13.277? What do you guys say? Left, right? It's less than 13.277, so it should be here. So what's the decision, guys? It didn't fall in the rejection region. What would be the decision? Fail to reject, exactly. Okay. So there is not enough evidence to conclude that the grade distribution for the department is different than expected. So you start. There is not enough evidence at the 0.01 level of significance to conclude that the distribution, all right, I'll show you screen, distribution of grades is different than expected. And that concludes the problem. These are the 5 steps, guys, that you have to do in order to do a goodness of fit test. This is how you do it by hand. Now I'm going to show you the calculator part. We'll see which one you're going to like better. It can be done on the calculator, but if a student have a very old calculator, a TI-83, maybe the test is not built on the TI-83, but it is built on the other calculators. So I want to show you the alternative way of doing this problem using the calculator. Okay, any questions about how did we make a decision to fail to reject HO? So we put the critical value and then our test statistic. If your test statistic, guys, you can write this down, is less than the critical value, you fail to reject HO. And if it is bigger than the critical value, you reject HO. That's how it's gonna work in this section. Okay, now let's do this using the p-value approach. Same question. Using p-value approach. Let me project this one right here. Okay, guys, the first step is whether you use a p-value or a critical value, you would have to state the same. The distribution of grades is as claimed above, the distribution of grade is not as claimed above, or you can say has changed. Either one is acceptable, guys. Now, using the p-value, let's do it together, guys. We're gonna do this together. You're gonna go to a test called, first of all, you're gonna go to stat, edit, and then you're gonna input the observed values in L1, and you're gonna put the expected values in L2. Okay, so let's do that. I already have the observed, stat, edit. Before you do that, let's clear the lists, guys. So I'm gonna clear, hit clear, enter. And then I'm gonna go here and hit clear and then enter. And L1, observed values in L1, guys, which are 42, 36, 68, 14. Now the expected values, you already done the work for the expected values. So you only need to do this, that's it. Expected values right here, just that. You have to do it by hand still in order to use the calculator. So what do I have? 40, 40, 64, 88. Let me write them down. So 40, 40, what did we say? 64, 8, and then 8, guys. All right, I'm done with the handout there. This is all I need. So this is L1. L1 again, guys, are the observed values, and L2 are the expected values. And how do you find the expected values? You take the percent from each category and multiply by the total. Percent times total, percent times total until you get them all done. This is how you find the expected values. I already explained that in the handout and how to find the expected values. So you don't need to take a note here. And now, guys, you go to stat, tests. I would scroll up if I were you because your test is right at the bottom. Can you guys see the test where it says goodness of fit? Right here. This is the goodness of fit test. Yep, you are right. So enter. Look how easy it is to use this test. Observed by default is an L1. Expected by default is an L2. You don't need to do anything. All you have to do, guys, provide the degrees of freedom. And can someone remind me again, what are the degrees of freedom here? Let's see. I'm not gonna, I'll see what you guys said. 4, I agree. Very good. Number of categories -1. Don't leave it as 2 or 3, whatever it is there, guys. You must change it. And calculate. You should not be surprised if you get 5.25 for the test statistic, guys, because we did it by hand. Bingo, 5.25. You can see that. And the p-value. So instead of critical value, you get the p-value. Let me record both of them. So we use chi-square goodness of fit test. And then chi-square is 5.25. And the p-value is 0.2626. All right, I'm done. More than alpha. Fail to reject HO. And then the conclusion, there is not, it's exact same conclusion, guys. There is not enough evidence at the 0.01 level of significance to conclude that the distribution has changed or different than expected. So it's still pretty much the same. Of grade is different than expected. All right, guys, so this is it for section 10.1. That's how you perform the test. Probably the question you will ask me, can we just use the p-value or critical value? Well, it depends. If I might be asking you, to do it both ways, but now you have 2 tools to verify the goodness of fit test. You can always use a critical value approach, but for the critical value approach, you need table 6 to be handy. If I were you, I will just print it out and keep it handy, just with me as I learn chapter 10, in case you need it. And for the p-value approach, you need your calculator, but you still have to do the expected values. So the calculator doesn't just do it for you. You have to do the expected values by hand because you have to put them in L2, put the observed values in L1, and just go through the process. Before I wrap this up, I'm just going to walk you through a couple problems. We're not going to do them, but I'm just going to show you that everything that you'll be working on is very similar to this example.